Hi, my name is Monica Diaz. I am an undergraduate student from University of Puerto Rico at Mayagüez. This summer, I'm doing research at the University of Florida as part of the SIR program at the Material Science and Engineering Department in Dr. Michelle Manuel's research group. My research this summer is focused on producing low-cost magnesium, calcium, and tin sheets for use in the automotive industry. More specifically, creating a magnesium alloy containing zinc, zirconium, calcium, and tin with mechanical properties similar to those of CEK100, a magnesium alloy containing rare earths. In order to determine the mechanical properties of the alloys, we perform tensile tests, from which we obtain the alloy's yield strength, ultimate tensile strength, elongation percent, Young's modulus. We also perform rigorous hardness tests, in which an indentation on the surface of the material is made and measured. This allows us to quantify the resistance of a material to plastic deformation. However, to understand why a material has certain mechanical properties, it needs to be examined at the microscopic level. This is done by performing optical micrography, which allows us to observe the structure of the alloy at the microscopic level. Also, SEM imaging of the fractures produced during the tensile test allows us to observe how the material fractures and if there are any precipitates that might have influenced it. The magnesium alloys that we studied had 2 weight percent zinc, 0.5 weight percent zirconium, and varying weight percentages of calcium and tin. The weight percent of calcium vary from 0.5% to 1.5%, and for tin it ranges from 5 to 10%. The ZEK100 alloy has 0.5 weight percent of REs, 1 weight percent of zinc, and 0.1 weight percent of zirconium. Another fact that was taken into consideration is how the heat treatment, culture, and a combination of both affected the mechanical properties of the alloys. Out of the different alloys that were tested, the 2 alloys with 5 weight percent tin gave better results for the tensile test. We were able to increase the yield strength when comparing it to ZEK100. However, as it can be seen in the graph, the elongation decreased significantly. In the case for the alloy with 1.5 weight percent calcium and 5 weight percent tin, the ASCAS sample produced the highest values of elongation, Young's modulus, yield strength, and ultimate tensile strength. These properties are most likely due to the formation of the magnesium, calcium, and tin phase that occurred in this alloy in greater amounts when compared to the other ones. In the micrography photos, we can see how the heat treatment slightly reduced the presence of this interface. On the SEM photos, the feather-like magnesium, calcium, and tin phase can be appreciated. In the alloy with 0.5 weight percent calcium and 5 weight percent of tin, the heat treatment of 500 degrees Celsius for 24 hours improved the elongation and Young's modulus, but decreased the ultimate tensile strength and yield strength. This was accompanied by grain growth. The average grain increased approximately 100 micrometers. In the SEM images, the phase magnesium, calcium, and tin is not as abundantly present. The hardness test for the ASCAS sample showed that the alloy with 0.5 weight percent of calcium and 10 weight percent of tin had the highest Vickers hardness value. This is consistent with the brittleness that this alloy exhibited during tensile tests. However, when cold work was done, the alloy with 0.5 weight percent tin showed the highest increase in hardness. Overall, the alloys with 5 weight percent of tin showed the best mechanical properties. In addition, certain tendencies like grain boundary definition can be associated with calcium and tin ratio. For future work, I would recommend lowering the tin to less than 5 weight percent and maintaining the calcium in the ranges between 0.5% and 1.5 weight percent.